Okay, so follow along as best you can while you're kind of playing around with molecules. Today's topic is kind of a summary on fossil fuels, and I want to bring my first slide back to what I mentioned yesterday. Um, I think it's important to recognize that all of the organic carbon molecules, um, basically, they come from something like crude oil. They come from drilling in the ground. Okay, and most 99, 95% of that is towards the heating industry, where you'd be using that for gas in your car or for propane in your barbecue tank or to heat your house, right? And for environmental purposes, yeah, that's definitely not necessarily environmentally friendly. However, I said this yesterday. I don't agree with anyone who would say leave all the oil in the ground, because there are other purposes for it. We can use it for other things. And this first slide I have right here kind of shows some of the things that you'd manufacture. Like, say, even just like the plastic in a helmet, the padding inside the helmet, it's probably based on some sort of carbon molecules. All those plastic Tupperware dishes, the comb, I mean, all of those are based off of organic carbon-based molecules. So not everything is like a fossil fuel that we use to blow things up and burn. So what I need to talk about today, though, is the process through which the manufacturing industry is developed. So it's not really a do; it's more of a just listen sort of day. So let's say that you want to separate some crude oil into different compounds, because not everything is gas that you burn in your car. Right? Here's a word I need you to know, or two words technically. It's called fractional distillation. Okay, and basically what they do is they separate the whole crude oil, all of the carbons. There could be carbons that have one carbon in them, methanes. There could be carbons that could have 8 in them, octanes. There could be carbons that have 70 of them, or 12, or 52. Right? You could have any number of carbon length chain, because you guys saw how yesterday you just add another one on, right? So the way you separate that crude oil is fractional distillation. The long and short of it is it's based on boiling point. Okay? Small molecules that have like one or two carbons, small molecules, they will boil off first. And so what they do is they put all of the oil into a big chamber like this. And what ends up happening is the really, really light gases, they boil off to the top first. So for example, any carbon that has, say, between 1 and 4, if you set the temperature to 20 degrees, it'll turn into a gas. Right? So that'd be like your methane, your ethane, your propane, your butane. And I think you guys even kind of know this, because methane and ethane are gases that we would use to like to heat your house. Propane is the gas you'd use in your barbecue. Butane is the gas you'd find in your lighter. Most of those are in like a gas phase if it's regular room temperature, right? But I mean, if you talk about heavier and heavier and heavier, can you guys see how the carbons? I know it's blurry on here, but the number of carbons is going up. That's, I think, 5 to 9, 6. Is that 5 to 9? Oh, it's 10 there. 10 to 16, 14 to 20. Anyways, the point I want to make is that in order to separate different types of petrochemical stuff, you separate them by boiling point. These ones are light, they boil earlier. These ones are heavy, they boil later. And they all have different purposes, right? From like propane in your tank, to gas in your car, to diesel or oil, or something that you might use for like a large factory or ship. Um, really, really, really big carbon chains. I think this says greater than 70. We actually use those to make roofing tar or to make asphalt for roads. If it wasn't for the petrochemical industry, we would not have roads, because roads are actually made out of really, really heavy carbons. That's all. So, long story short, no fractional distillation. It's all about boiling. And here's another picture of the same sort of concept. The lighter, the smaller compounds, they go to the top of the tower, and then the heavier ones stay at the bottom. So that's how they separate them. Well, once you separate them, then there's also other things you can do with your chemicals. Kind of like how you guys are playing around and saying, well, what if I attach this, and what if I do this? I mean, that's really what chemists and scientists do, is they play around and they try to make something new, right? All of a sudden, one guy discovers they made TNT, and another guy discovers he made aspirin. So here's a few different words that I'm supposed to make sure you're aware of. One of them is called cracking. Okay. And if I could, I'd like to steal someone's molecules for a second. Can I steal yours? Okay. And can I steal those other ones there? I'm just going to put them all together. So imagine that this is one really long molecule here. And that you drilled this molecule out of the ground, and this is a, let's count them up here. 1, 2, 3, 4, 5, 6, 7, 8. So this would be an octane. Okay. Well, sometimes what you might want to do is have smaller molecules than octane, because octane is just too big. You can't use an 8 chain. What you might want to have, Oh, that was pretty close. That's a 7. Let's just use the one on the board. See how the one on the board has 7 carbons in a row? What may end up happening is if you heat something really, really hot, you can actually cause it to crack. And what ends up happening is this one kind of falls off of there, and it gives you like a 5 in a row. And then this would loop back onto here and create a double bonded molecule. And you end up getting smaller pieces, basically by just like ripping it apart. And if you can see what happened there, it ended up creating the 5 in a row, and it created the 2 with the double bond. Let me show you that one more time here. So here's kind of the logic behind it. It used to look like this, 7 in a row. Well, if we heat it, superheat it, called cracking it. I mean, cracking basically means cracking into pieces, right? Then what could happen is this could rip off like that, and then create a double bonded molecule. Now, this particular one that I showed you went 5 and 2. But it doesn't have to go 5 and 2. You might also get something that might do this. So it might do a 5 and 2. It could do a 4 and 3. All right. Long story short, cracking occurs so long as it gets separated into smaller pieces. So if you have a large molecule, a long molecule, and you break it into pieces, that's known as cracking. And on the next slide, I've got some more pictures of the same concept here. Here's your hexane, and to crack it, you just basically break it into 2 smaller pieces. Or this one I found, this is dentane, breaks into, actually this one broke into 3 pieces. You don't even have to break it into 2 pieces, into 3. Now, sometimes you might come across the word called hydrocracking. If you have hydrocracking, what they do is they add hydrogen as a reactant. And I want to show you what that would do. If you added H2 gas, you see how right here there's kind of a gap where there's kind of some missing hydrogens because of the double bond? Well, if you add some hydrogen gas, what would end up happening is it would kind of fill in the gap so that you don't have to have double bonded molecules. And the term we use for that is saturated. I don't have it bolded here, but saturated is the word I want to use. Okay. Now, yesterday in our notes, there was a slide that I kept skipping over for each one of the ones. There was a word I needed you guys to know from there. I probably should have pointed out. It's called saturated. A saturated molecule is full, which means that there's no more room for any more bonds. All of the bonds are taken up. All the slots are filled in. That's a saturated molecule. Long story short, if it's an alkane, it's full. If it's only got single bonds, everything's good. I'm going to steal Sarah's molecule for a second. See how there's a double bond on there? Well, this double bond would not be considered saturated because it's very possible to do this instead. Rather than have this double bond right here, this is considered unsaturated. But if I were to bust up the double bond and attach something there instead, now it's saturated. Should I show that one more time? This is considered to be an unsaturated molecule. It's got a double bond there. And that double bond, what you could do is bust up the double bond, put something else in its place, and you can add more to it. Can I add anything more to this? Well, no. This guy's full up on stuff. This guy's full up. Everybody's full. But if you can see this guy right here, see how this double bond right here, there's like an open space right there? If you can add hydrogen to it, it's called saturating a molecule. So anyways, long story short, that's known as hydrocracking. If you break something into pieces, and then any gaps, you fill it in with hydrogen, that's hydrocracking. It's actually very similar to another word I need you guys to know. It's called hydrogenation. Hydrogenation. There's not supposed to be a T there. I spelled that wrong. Hydrogenation. And that's more or less the same thing I just mentioned here is, let's say that you have a molecule that has a double bond. It's just like what I showed you right here, more or less. Here's your double bond. Well, it's not considered full or saturated because what you could do is you could bust the double bond up and put some hydrogen in the open slots. Well, that's what happens here. This double bond right here gets busted up, and then this guy takes a hydrogen, and this guy takes a hydrogen, and then it makes what's called a saturated molecule. So, long story short, what makes something saturated? Which means that there's only single bonds left. If it's unsaturated, it means that you have double or triple bonds. That's all. And then what compound do you need to add to make something saturated? Hydrogen gas, yeah, H2. There you go, that's it. Okay, the next thing I want to talk about is how when they make these smaller molecules, they can actually put them together into something called a polymer. Maybe you've heard that word before somewhere. A polymer is based on a monomer. Okay, it's based on the way the word works. You guys know that poly means more than one and mono means just one. So the way polymers work is that they're repeated sections based on individual links. You have like a little monomer, like a one section thing, and if you repeat it over and over and over and over and over and over and over again, it makes a polymer. And most of these things are synthetic. They're not naturally found. They've been found in the lab. I want to show you some pictures here. This right here is this is called a propene. You guys remember what propene is? It's 3 carbons, but the ene means there's a double bond. So look at this molecule right here. See how it goes 1, 2, if I kind of go around the corner, see how there's 3 carbons right there? And if I were to add another one of these guys like this, and another one of these guys like this, and find a way to add them all together. Usually heat is what does it. If you add some sort of heat and add them together, it ends up busting up all those double bonds. See how there was a double here, there was a double here, and there was a double here? And instead, in between, it started putting a single and a single in between. And it makes a really, really long repeating chain. Where, can you guys see how this right here is based on like that one right there? And then this section right here is based on this section here. And this section here is based on this section here. It ends up making what's called polypropylene. And you guys probably know what polypropylene is. It's this.
Plastic?
It's plastic. Yeah, it's plastic bag type stuff, right? So you had a propene here a second ago. I'm just going to rip yours up a little bit here. Sorry. This would be a propene like this. 1, 2, 3 with a double bond there, right? And if I were to get a second one of them, like this, what ends up happening in these polypropene molecules is they bust up the double bonds. So imagine I'm going to rip out this double bond right here, and I'm going to attach this guy here. And then I can do that again. I can rip out this double bond right here and attach a new guy right here. And the idea is you should be able to do this infinitely. Right? So if this picture makes sense, I'll even find another one here. Let's go to this one right here. This is tetrafluoroethene. See how there's a double bonded, a double bonded, a double bonded? And what ends up happening is you bust up the double, make a single, make a single, make a single, and then start linking them together. It basically makes a process that can be repeated infinitely. It can just keep going on both sides for forever and ever and ever. And these make some pretty cool compounds. This is a tetrafluoroethene, and it made polytetrafluoroethene, which is Teflon. You guys know what Teflon is? What do you put Teflon on?
Isn't that ceramic?
Nope. It's used in the kitchen, though. No. Sometimes it goes on frying pans. It's the coating that goes on non-stick frying pans. That's what Teflon is. It's used to make it so that, like, when you're making an omelet, you don't have to, like, coat the pan in grease or butter or olive oil or something like that, right? It should be non-stick. That's what Teflon is. This one right here is ethylene. This one down here is polyvinyl chloride, which is PVC piping. And hopefully you can kind of see the pattern. There's a CCHHHCl group, and then there's another CCHHHCl group. And all you do is you just take these double bonded molecules and you just kind of shove them all together and make a self-repeating pattern. So I mentioned this one yesterday. These are the monomers. So monomers are the individual packets that like get shoved together to make the big repeating section. This is PVC. This is Saran wrap. Look at this. The only difference is that in Saran wrap there's 2 chlorines, and in PVC there's 1 chlorine. That's all it takes. 1 chlorine difference, and it goes from being a hard, rigid plastic to being really flexible plastic. Okay. So, this is acrylic. This one's kind of cool. This one's crazy glue. And if you just add a second one of it, like this, and you just keep repeating it here and here and here on both sides, break the double bonds, and just fill in the gaps, it makes a polymer. So a lot of the stuff that we use nowadays is actually polymers. So again, this kind of comes back to my talk about how we can't leave all the oil in the ground, right? It makes this, it makes this, it makes this, it makes this, right? It makes so many things. It probably made the fabric if there's like polyester there, right? Polyester clothing is made from multiple esters being put together if you learn what an ester is one day. So anyways. Okay, so last thing I need you guys to know how to do. Although I mentioned the petrochemical industry does contribute to manufacturing, the main source of what we use oil from the ground for is to burn it. So we do need to talk about the one reaction type that matters here, which is combustion. So you guys need to be really clear on how combustion works. It always involves a hydrocarbon. You always add it to oxygen, and it makes carbon dioxide and water. So I need for you guys to be able to write and balance and work with the combustion equation. So if you guys want to just set the stuff aside for just 1 second here, let's do our last examples and we'll call it a day. So here's kind of a picture showing combustion. This would be like methane. If you guys want to take a look at this for a second, look how methane works. It's C with 4 H's. And then this oxygen must be O2, right? Because oxygen comes in groups of 2. Then all of the bonds break. Right? Every single bond breaks. So this one, this one, this one, this one, that one, that one, that one, that one, they all break. So all of these molecules have no more bonds anymore. And then we rearrange them around. So like this carbon takes that oxygen and that oxygen. And this oxygen takes that hydrogen and that hydrogen. This oxygen takes that hydrogen and that hydrogen. And they've now rearranged. They made something new. So here's the task. It's not overly hard, but I need to be able to do this. Can you write a balanced chemical equation for the combustion of hydrocarbons? So this is the first one. We need to combust pentane. Well, it always works like this then. So if you want to write out the one for A, the combustion of pentane will be pentane plus oxygen will turn into H2O and CO2. Yeah, go for it. It's kind of the only thing we needed a pen for today. So, okay, now it's just the thing that goes in this line right here. It's going to change every time. So we need to know what's pentane's formula. So how many carbons does pentane have? Okay, any double bonds? No, because it's an ane. Okay, so we know it's going to be C5. Then the question is, well, how many hydrogens does it need? So in the process of writing out this question here, you need to be able to draw it. Because if you can't draw it, you don't know what its chemical formula is. You know what I'm saying here? So we know there's 5 carbons. How many hydrogens do you need? Often what I'll do as a shorthand is I won't actually write out all the hydrogens. I'll just put a little dash where they'd go. So we'd need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You're right. So it's C5H12. Okay, well, now that we know what pentane's formula is, now we just need to balance it. So, okay, so to balance, we need 12 hydrogens, and there's only 2 over here. Put a 6 here, yeah, because then 6 times 2 gives you 12. We need 5 carbons, but there's only 1 over here. Put a 5 in front of it. Okay, then we need to take stock of our oxygens. 5 times 2 gives you 10 oxygens. And then 6 times 1 gives you 6 more. So 10 and 6 is 16. But oxygen has to come in groups of 2. So we need 16 total, but they come in packages of 2. Means you need 8. There you go. Now it's balanced. So that's the sort of task I might need you to be able to do. That's it. Let's try a few more. Let's combust 2-pentene. So if I want to write this out again, it's an unknown molecule plus oxygen makes water. Some more room here. And carbon dioxide. These parts here, they never change. Just the question is, well, what the heck is a 2-pentene? Okay, well, pent is 5 again, right? So 1, 2, 3, 4, 5. What's the 2 mean? Not a branch, there's a double bond on the second one. Yeah. Good try, though. If it said, like, methyl in front of it, that's the branch. But the ene means the double bond. So I don't care which side I pick, but after the second one, I need a double bond. So I'm going to go 1 here, 2 here. So there's my double bond. This is now considered to be an unsaturated molecule. It's not going to be full of hydrogen. Like, if I start putting hydrogen lines everywhere, there's room for, like, 1, 2, 3 around that carbon. But this carbon right here already has 3 lines around it. So it only needs 1 more. Not 1 down there, that'd be too many. And this carbon right here already has 1, 2, 3 lines around it. So it only gets 1 more, doesn't get 1 down there. Then this one needs like 1 top and bottom, and that one needs top and bottom on the side. Can you guys see how there's kind of a gap right here? That's where it's unsaturated. If I had more of these to play with, that's where I would literally take like that one there. I'd rip it apart, and I could throw another hydrogen on the end. Right? So, anyways, we know we need 5 carbons. How many hydrogens are there then? count them up. How many? Yeah, I think there's 10 as well, because you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Really, you're missing 2, right? Okay, so now let's balance this one. Okay, so we know we're going to need the 5 carbons right here, so that solves that problem. And then for my hydrogens, I need 10 of them, which means in front of this hydrogen right here, I need a 5 as well. We actually come into a problem, though. In terms of oxygen, then you have 10 oxygen over here and 5 right here. 5 and 10 give you 15, but 15 doesn't divide by 2. What do you do to solve this, do you know? Sweet, double everything, yeah. So you put 2 here, scratch this out, make that a 10, and make that a 10, make it twice as big, and then now reconsider this. Now you have 10 oxygens, and then you have 20 more over here, giving you a grand total of 30. 30 does divide by 2 to give you 15. Now it's balanced. Sweet. Okay, C. 2,2-dimethylheptane. So why don't I draw it out first here? 2,2-dimethylheptane. Hept means 7. 7. Hept is 7. Hex is 6. So 1, 2, 3, 4, 5, 6, 7. Okay, on the 2 and also on the 2 we need a methyl. So I don't care which side we go from. Why don't I do this side over here? 1, 2. I need a methyl going up. I need another methyl going down. And then now I just need to start counting out hydrogens. So I need like 1, 2, 3 on that guy. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You guys can handle that? So it means I need 20 H's. How many carbons are there? No? How many carbons are there? 7's only in the main branch, though. I know it's a heptane, so you think there's 7, but 8, 9. Yeah. So good learning moment here. Don't just count the ones in the main branch. Don't just say, oh, hept, that means 7. Don't forget to count the branch carbons too. Those count. So it was C9H20 plus O2 makes H2O and CO2. Now we just got to balance it. Okay, C9. So that means I need 9 carbons over here. H20 means I'm going to need 10 to get my hydrogens to work. Let's see. You got 10 oxygens plus 18 more. Gives you a total of 28. But they come in groups of 2. 28 divided by 2 would be 14. You guys do that? All right. Why don't I just do one more of the last ones then? Let's just do the very, very last one. E. Now there are still some names that are like they have a formal name. The 2 you should probably know are glucose and sucrose, which are essentially sugar type molecules. So you can still combust these as well. We actually did this in the fume hood. I combusted a gummy bear. You guys remember that?
Was it a
Oh yeah, it was a jujube. It's sometimes you use gummy bears, but I think Miss McCarthy had jujubes that day. So it wasn't that I melted the sugar, because like you could go to the stove and literally burn and melt sugar. That's not what we did. We blew it up, and it released so much energy in part because it's such a big molecule, right? All the other molecules we're talking about are a little bit smaller in scope. This one is massive. It had so many bonds to break, and as those bonds broke, it released a ton of energy, and that's why it was like a white. I think there was even like some magenta color to it, right? Like it was pink. So, all right, so let's do this last one, then we'll call it a day. So we're going to take C12, H22, O11. We're going to add it to oxygen, and we're going to make water and carbon dioxide. Now, one of the twists to this one here is that we actually have oxygen in 2 different locations. You guys see how there's oxygen here attached to the molecule itself, and right here? We have to account for that. But let's do oxygen last. Let's deal with the other molecules first. So if we have 12 carbons, well, then let's put a 12 in front of the carbon dioxide. Okay, solves that problem. And if we have 22 hydrogens, there's 2 of them over here. 22 from 2 means you need 11. Still good? Okay, now this, in terms of oxygen, there's 11 right here. 11 oxygens on this one. And then there's 12 times 2 over here, which is 24, giving us a grand total of 35 oxygens over here. Which means this side over here better have 35 as well. However, there's 11 in this guy right here. So there's already 11 on this guy right here, which means we need this oxygen to make up 11 plus what equals 35. But isn't it just 24? Don't I already see right here that 11 and 24 makes 35? If 11 of them are right here, then there better be 24 out of this guy. And if this guy comes in groups of 2, you need 12. There we go. All right. So in terms of this organic section, I don't know, maybe 4 things I need to be able to do. Thing 1, if I give you a name, can you draw me a picture? Thing 2, if I give you a picture, can you give me its name? You handle those 2 things. Okay. Thing number 3, do you know some of the words that I gave you, some of the definitions to describe some of the manufacturing processes we use to make new chemicals? So some of those words would be fractional distillation. What does that mean? It's fractional distillation. Heat it up. Lighter stuff boils off first. Heavier stuff doesn't boil as fast. That's how we can separate them based on weight. You can also do things like cracking a molecule. What's cracking a molecule do? Breaks up a double bond, breaks it up, and probably gives it a double bond and makes it smaller, right? Hydrogenation fills in a double bond gap. So double bonds mean that there's like an open bond right here. You could bust this one open and then add something to it. So that's hydrogenation. You should also know about things like monomers and polymers. Monomers are small little pieces that if you did this one and this one and this one and this one and like link them all together, then it makes a polymer. That's all. You should know that these molecules, they make a lot of really cool, useful things. Even Sarah's kind of looking through my book here. This came in one of the molecule kits. It kind of shows you some different molecules you can make. This one here had vanilla and aspirin, and I'm sure there's even more. Vanillin. Well, it's vanilla. Vanillin is the main thing in vanilla. This is ethyl alcohol.
Ooh. Alcohol.
This is propylene. Yeah, this will give you some cool ideas. Okay, that's the third thing you should know. You should know some of the definition words. And then the last one, can you write a chemical equation using these things? Most likely, the chemical equation is going to be combustion. What does combustion always involve? Take your carbon thing, add it to oxygen, and it always makes water. So there you go. And then can you balance it? So that's it. That's our chemistry unit. Kind of 3 sections. Section 1, all about the math about solutions. Section 2, almost all theory in terms of knowing your oxidizing, your reducing agent, how to use that table, and batteries basically. And then section 3, can you name some of these new cool chemicals that you're just playing around with right now? All right. Why don't I leave it there? Here's the plan going forward then. Tomorrow's a work day. When you guys come back from May long weekend, we're going to write a quiz, have another work day, and then do a unit test. And then we got to go on to the geology rock unit. Rocks. So, okay, so things you guys should work on then. If you have any labs that you haven't done, work on those. If not, there's 2 assignments, and that's all we've got left to do. So I know a couple of you have finished the first one, right? You finished the first assignment? You finished the first assignment. You guys finished the first one? And you were just about done. Okay, so get started on that second assignment as soon as possible, though, because it's kind of your practice to help you learn this stuff, okay? So maybe play with the things for like 2 more minutes or so, finish up what you're doing, and then move on to something else. I have no idea. That's the cool thing about organic chemistry is that someone has an imagination and says, hey, let's just play around, and then they discover that it's Kevlar, or that it's aspirin, or that it's, right, like, yeah, you just discover cool new things. This is what makes chemistry a lot of fun, actually. If you say school's not fun, no, like chemistry can actually be a lot of fun. Designing and making new things. Okay, I'll leave her there. Let me know how I can help, okay, guys?